Section 16.1 in both Stewart's and Thomas's textbook. First, let me give you an introduction of what vector calculus is. Vector calculus is differentiation and integration of vector fields primarily in R3. Vector calculus is also known as vector analysis. This topic, vector calculus, that means this chapter deals with the following topics. We're going to learn about vector fields. We're going to talk about two brand new integrals, namely line integral and surface integral. We're going to learn three important theorems, namely Green's theorem, Stokes' theorem, and divergence theorem. But first, let's see what a vector field is. What is a vector field? Vector field is a function that assigns a vector to each point in either R2 or R3. In other words, each point in R2, which is what? A set of ordered pairs, will result in a vector. And each point in R3, which is ordered triple of real numbers, will result in a what? Vector as well. The notation is capital F with an arrow on top. That means this is a vector field. And the x and y components are some function of x and y. So these are components function, which they happen to be a scalar. You can also write it as linear combination of I and j. So you can write this as pi plus qg. So in 2D, for every ordered pair you select vector field, which is a function assigns a vector, it generates a vector. So at this point you got this vector, at this point you got this. So collectively you have what? A set of vectors on the floor, which is xy plane. So that would be the picture of a vector field in 2D. In 3D, you have what? The components of the functions are functions of x and y and z. So you got p, q, and r. For each what? Ordered triple in R3, you get a vector. So a collection of vectors in R3 based on what p and q and r is known as a vector field in R3. So let me show you some pictures of what? Vector fields, so you get a gist of how vector field looks like. Notice this is a vector field in R2, which has y as first component, x as second component with a negative. Notice the vector field is rotational. Do you see it? It rotates about the origin. So this is a picture of a vector field for this particular vector field. So this is the picture of this vector field. The other one is x squared I plus yj, and this is how the vector field looks like. Do you see it? So this is a picture of vector field x squared comma y. Vector field can also appear in 3D. So there you have it. So this is a three-dimensional vector field, and the x component is sine, y component is cosine, z component is xz, and this is how it looks like. Do you see it? It's all collection of vectors in 3D. For every x and y you select, incidentally, x goes from 0 to pi over 2, y goes from 0 pi over 2, z goes from -1 to 1. This is how the picture looks like. So the other picture, which is pretty much the same as the other picture, except I took the arrows out so you can clearly see how vector field looks like. Correct? So question is, where exactly vector field shows up in real life? Well, vector field, examples of vector fields could be a velocity field, force field, gravitational field, magnetic field, acceleration field, you name it, it shows up in real life. For velocity vector of a flow of a fluid around like in this case, this is of a flow of air around an airfoil in a wind tunnel. This is the type of experiment which aerospace engineers do in their labs. So it's wind tunnel labs. The other one is streamline, which is the flow lines in a contracting channel. That's like moving water moving through a channel, like through a pipe or something. So, so that would be an example of velocity field. Force field associates a force vector with each point in the region. So this could be like force times mass is acceleration. Excuse me, mass times acceleration is force. Gravitational field, so that would be like gravitational attraction. So that would be an example of vector field. Vector field could also describe counterclockwise rotation, like so. And the equation of that vector field is negative yi minus xj. Notice, so the arrows might show up in a rotational manner. This would be the fluid flowing steadily, what? Along a pipe. And if v represents the velocity of this whatever fluid is at any given point, x, y, z, so v is a vector field, velocity is a vector field, and the speed of the flow at any given point is the length of these arrows. So that would be an example of a vector field. One of the special fields, vector fields, is called gradient field. You know what gradient is. If f is a scalar function in 2D, then the gradient is what? A vector whose components are partial derivatives. And in R3, it will be like partial derivatives of f with respect to x and y and z. This is also considered to be a vector field. It's a special kind of vector field. It's called gradient field. Remember, this guy points to the what? To the fastest increase direction of f. And it's also, if you recall from previous chapters, is perpendicular to any level curve at any point on the curves. So the picture of the gradient will look like something like this guy. Right? So suppose this is scalar function, x squared y minus y cubed. The question is, plot the gradient vector field together with the contour map. How are they related? Well, here is the gradient field. So this guy is called gradient field, a gradient vector field. All right, this is how it looks like for this particular scalar function. This is the level curves. That's like if you set x squared y minus y cubed equal to k. K is a constant, correct? K is a constant. So these are called contour maps. What I did in the last diagram, superimpose the gradient vector field with the level curves, and this is what I got. I don't know if you guys can see it or not, but for instance, in this particular region on top of the graph, this is basically how what the gradient field kind of intersects the level curve, but at the point of intersection, they are like 90 degrees. I don't know if you guys can see it. So the relationship between the gradient vector field and the level curves is the what? Vectors in the gradient vector field are perpendicular to the level curves at any point on the level curves. Do you see it? As a matter of fact, that was one of the properties of what? Gradient vector, which is what? Perpendicular to what? Any level curve at any given point. So that's primarily a quick overview of what vector gradient vector field looks like. And with that said, so in the next video, we'll talk about more about vector field and its application in real life. Thank you.